Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 34. And this problem gives us the stick and ball models of A on top and B on the bottom, and it asks us to draw the products formed when we reacted with reagents A, B, and C, or 1, 2, 3. First one being bromine and Lewis acid, second one being nitric acid and H2SO4, sulfuric acid, and the third one being Friedel-Crafts acylation reagents here. So the first thing we need to do is identify the directing groups of the substituents on our benzene ring. So on the top, we have an electron donating group because of the resonance that can be formed with this oxygen donating electron density into the ring and actually forming a carbanion in the benzene ring. So we know that electron donating groups are ortho and para substituting. So ortho, and I'll highlight this in blue, and para substituting. But the para group is actually occupied by this aldehyde. So we're only directing ortho. Next, and actually the position of this aldehyde is actually off. So let me just redraw this. So the aldehyde is actually in this location here. So we actually do have a para position which we are directing. The aldehyde, however, is an electron withdrawing group because of the electronegative oxygen atoms. So we know electron withdrawing groups donate or direct at the meta position. So we only have one meta position. However, we have now opposing effects. So we have two ortho, one para from this oxygen, and then just this one meta from this aldehyde group. However, in terms of the strength of the directing group, we know that because of the resonance that can be formed with this oxygen causing a full negative charge in the benzene ring, this alkoxy group here is this much stronger directing group. So we know that this direction from the ortho and para is going to outweigh and be stronger than the direction of this electron withdrawing group aldehyde group here. So we know that we will follow the ortho and para direction of this alkoxy for all of our reactions here. However, we know that this ortho position being between the two bulky substituents, we know that there will be no substitution at this ortho position because they're in between these two bulky groups. So the sterics is going to prevent any chemistry occurring at this carbon here. So what we will end up with is a product that will be at the ortho position and an isomer that will be at the para position. Now for this group, we have this oxygen that has electron rich is going to donate electron density into the ring, and therefore we know that it's going to be ortho and para substituting or directing, but the para positions occupied in this example. And we know that this amine, also with the lone pair electron, can donate resonance and electron density into the ring to make a full carbanion in the carbon ring. So know that this is also going to be electron donating to its ortho and para positions here. However, once again, a negatively charged oxygen is far stronger of a directing group than an amide. So because of that, we know that we're actually going to be following the ortho position of the stronger directing group, which is this negatively charged oxygen atom here. So with the location of the substitution identified, the rest is easy. So for A, when we have halogenation, we know that we're going to add a bromine to the ortho and para position of A and to the ortho position of B. So we're going to have one isomer with the bromine at the ortho position plus one isomer with the bromine at the para position. And then for B, we're going to have just one isomer with the bromine at the ortho position. The two ortho positions are identical because of that internal plane of symmetry. So it doesn't matter which one I draw it in, they're both the same. They're both identical. So I'll draw it at this position here. Now we have nitric acid and sulfuric acid. So we know that we're going to add a nitro group to either A or B. So we know that, once again, because we already identified the positions that our substituent is going to add on, or our reagent is going to add on, the rest is easy. All we need to do is just fill those in at the appropriate position. So for A, we'll have two isomers once again. One being NO2, one being the ortho-derived product, and an isomer being the pair-derived product here. And then for B, because we only have that one position that can have some sort of substitutions or chemistry, we know that I'm drawing A again. Let me draw B. We know that the nitro group is going to add to this carbon here. And now for the Friedel-Crafts alkylation product, once again, we'll draw the products of A here. So you draw your benzene ring. And now we'll add the acyl group with 1, 2, 3 carbons. So this is 1, 2, 3 carbons at the ortho position, but we'll also have an isomer at the para position. With 1, 2, 3 carbons as well. And then we'll also have B with this acylated product at the ortho position here. One, two, three carbons. Perfect.